Good afternoon, everyone. Thank you so much for joining us. We're broadcasting from the Glennon Auditorium at NASA headquarters, so this is a bit of a last-minute change of venue, so bear with us. I'm Abby Ryman. I'm a space plasma physicist and outer planet expert on a rotation at NASA headquarters from the Johns Hopkins Applied Physics Laboratory. So today NASA XD are bringing you a talk on the dust in our universe. NASA XD stands for NASA Constitutional. It's conceived to be a place for us to have the sort of conversation that you might overhear in a conference bar. It's the kind of vibe that we're going for, unapologetically high-level, freewheeling scientific conversations. Our audience is intended to be the community of PhD-educated or equivalent scientists who are funded via programs such as NASA Roses. But we also hope that it might be a place that any scientifically literate or interested person might land to get a feel for how NASA scientists conduct our conversations, place to set a good example of the best of measured, informed, data-driven debate. Another motivation for our project is the observation that there is no money in the Science Mission Directorate. All of the money is in the NASA divisions. That's how we allocate funding, and that's how we fund almost all of the amazing projects that NASA is so successfully doing. So as I mentioned, our topic today is cosmic dust, and to host and guide today's conversation, I'll hand you over now to NASA program scientist Arik Posner.
So my name is Arik Posner. I'm a program scientist in the Heliophysics division, and I also welcome you to NASA headquarters in this late January afternoon, here in the audience and also, of course, online. I have the great privilege to introduce to you Dr. Vere Stacken from the Eidgenössische Technische Hochschule in Zurich, Zurich, Switzerland. Vere was actually born in Ghent, Belgium. She started her studies at the Technical University of Delft in the Netherlands, continued doing aerospace and systems engineering at ESA's ESTEC facility in Noordwijk, in the Netherlands, where she got involved in advanced mission concepts. She is very shy about it, but she did work on an early version of the Interstellar Probe, which is, of course, now a very interdisciplinary subject being discussed among scientists in various fields. From there, from these studies of systems engineering, she got confronted with the problem of interplanetary dust. And that fascinated her so much that she actually changed to turning into a science PhD, which she did in Germany at the Technical University of Braunschweig and the Max Planck Institute for Nuclear Physics in Heidelberg, Germany, where she studied under Professor Dr. Jean-Marc Rued, who I also had the pleasure to be taught by for a year. I admire Professor Rued for not only his achievements as the founding father of astrophysical dust, but also for his humanity. After her PhD in 2012, Dr. Stärke moved on to Switzerland, worked at various highly reputable institutions, including the University of Bern, the International Space Science Institute. She worked also in science administration at the Swiss National Science Foundation. And now she's employed at the ETH in Zurich, where she leads a group funded by the European Research Council. She recently also got awarded a prize to be given out every 3 years for a Belgian national working abroad in the field of science with exceptional achievements. Without further ado, I'd like to pass on the mic to Dr. Vere Stacken. I'm looking forward to this.
Thank you very much. So first of all, I would like to thank Dr. Posner and Abigail Ryman for the invitation. It is truly a pleasure to talk here at NASA about dust. It's always a pleasure to talk about dust.
So I'm going to talk today about interstellar dust and the heliosphere, especially because there is a lot of cross-divisional science to do in this field. Before I start with that, I would like to give a small little introduction of my humble team, I would say. We have two fantastic postdocs. One has left but will be replaced, and the other one is still with us. We have a contractor, and they are doing a lot of work that you will also see in this presentation. And we also have a couple of students, master students, bachelor students, who are working with us. Now, the dust science that we do is actually in itself already almost interdisciplinary, I would say. So the first thing we do, the biggest thing we do is simulations of dust. And apart from that, we also do instrument calibration, because you need to know how the instrument responds. We do development and characterization of dust analogs, actually in collaboration with another team inside of the ETH in Zurich. And usually that team works for medical science, so you see already quite a lot of cross-disciplinarity in here. Then we have spacecraft data reduction. I will explain more about that in this talk. And we have mission concept design, especially since I'm an aerospace engineer myself. So today, actually, the main take-home message, even though some of you are at home already, but the main take-home message is it's not just about dust. It is about more than just dust. And I'm going to talk about interstellar dust and the heliosphere. I'm not going to talk about interplanetary dust, although it is at least as fascinating. I'm also going to talk about synergies, not only between science fields, but also between measurement techniques, and then finally also synergies between different missions. For this, I have to take you to Switzerland, where I live and study and work. We're here in the mountains in Switzerland, and you see here the Milky Way here with these black patches in the sky. And these black patches, that is not that there are holes in the sky, as William Herschel used to think. This is actually dust, interstellar dust that is blocking the light from the stars. Now, if you look at a top image, this is an artist impression of the Milky Way here. If we are here with the sun and the Orion arm, and one galactic year is about 220 to 250 million years, and we turn around the galaxy in that time, and we cross a lot of regions with different densities of gas and dust. So it might be that we have passed a few thicker dust clouds in the past. Now, to put this in a perspective of time, this is the last round, the last circle we made, the last orbit. And you see here the dinosaurs when they were living. This must have been 65 million years ago when the last one had been extinct. So just to give you an impression of what it means in terms of time. If you zoom in on that image, this is here an image of, or an artist impression of about 20 light years around us. You see here the sun is moving in the direction of a certain cloud. We are in the local interstellar cloud here, and we're moving at 26 kilometers per second in the direction of a so-called G cloud. And we are lucky because we're now in an intermediate region, which is called, well, it has no name for it, but we're basically going from the local interstellar cloud to the G cloud in the next couple of thousand years. And we've been in the local cloud for 60,000 years. And so one of the questions that one of my colleagues, Jeff Linsky, has asked me is, hey, Vela, have you seen with your spacecraft any dust particles that came from another direction than the usual direction in which we're moving? That's a very interesting question. It's very exciting. Now, if we zoom in again on that plot here, we get here the solar system. We have the sun in the middle, the planets, and the sun is expelling a lot of solar wind, ions and electrons. And this is happening at 400 kilometers per second. At the same time, this bubble of the sun is moving through the interstellar medium. So we have actually the gas and the dust from the interstellar medium coming through the solar system. There are only two spacecrafts that have flown outside of this bubble, which is called the heliosphere, and that's Voyager 1 and 2. So we have actually only two line-of-sight measurements, well, not line-of-sight, two lines that the spacecraft crossed through. And unfortunately, they didn't have a dust detector on board, but they have done fantastic discoveries so far. And they're still sending us data. Now, the heliosphere is actually, we don't know that much about it yet. There are quite a few problems that we have. And the first one that is a big discussion in the heliosphere community is, what is the shape of the heliosphere? We don't know, theoretically, if it is a cometary shape, if it is like a spherical shape, or rather a croissant. And these are really big discussions that are going on, and it's fascinating. Then the other thing is the heliosheath thickness. The heliosheath is the region between the heliopause and the termination shock. It's this region here. Why is it so thin? All the models would predict that it's a bit thicker. Then also the magnetic field inside and outside was in the same direction. They expected it to change, but that didn't happen. And there are many more questions about the heliosphere. So the heliosphere scientists, I don't consider myself a heliosphere scientist, but I do a lot of conversations with them. We work together. But they say this is an example of very beautiful cosmic terra incognita, and it's just outside of our door. It's just outside. This is our neighborhood. We don't even know how it looks like. Why is it important? Well, it is actually important. It is, first of all, the medium through which we are looking. If we look at the other stars, so you need to know what you're looking through in order to know what you're looking at. Second, it's a proxy for astrospheres, and this is important for exoplanets. As a matter of fact, I have to return home tomorrow because next week there is a meeting in Germany exactly on this topic, exoplanets connected with heliosphere science. And this is already interdisciplinary. This is cross-disciplinary. Then the heliosphere is a giant plasma physics laboratory. The discussions that are going on are on the plasma level, on the physics level. It shields us from galactic cosmic rays, so it's important for the evolution of life, and it may even affect the climate on our planet, and thus also of exoplanets. So I have put here already a few of these cross-divisional science themes: exoplanets, plasma physics, Earth history, and these are just a few for the heliosphere science. Then we have the dust. Why is dust important, or interstellar dust important? Well, first of all, it is what we are made of. When dust scientists, we go for a beer or a drink or so, we don't say cheers and we don't say Gesundheit, we say dust to dust. It reminds us of what we are made of, and it's actually very philosophical. It's nice. But it's also essential in the interstellar medium. It's, for instance, essential for astrochemistry because, for instance, two H atoms can come to the dust surface, they adhere, and then they migrate, they bond, and they desorb again, so you have an H2 molecule. And also more complex molecules form in interstellar space. It's also important for the temperature of the dust clouds there. It's important for shielding of molecules from UV from the stars. So that means that without the dust, you wouldn't be able to form a molecular cloud and then a collapse and then a new star and planet. And the astronomers are also interested in this topic because they need it for their observations. Again, they look through this dust and they need to know what's behind, so they want to know what they're looking through. Some of my colleagues who do modeling of dust disks, they also ask for the properties of the interstellar dust. And finally, it is also a piece of the puzzle of the heliosphere, and this is actually quite new. Why? Because dust and the heliosphere is connected to each other, and I will explain that in this talk. So we use dust for learning about the heliosphere. It is often an overlooked part in the heliosphere physics so far, and we are actually right now just starting to explore that, the whole heliosphere community worldwide. And we also need the heliosphere for the dust. So we need to exchange with each other, and we need to have cross-divisional exchanges, basically. So here are again some cross-divisional words, science themes: exoplanets, astrophysics, astronomy, heliosphere, astrosphere, plasma physics. It's getting already a big mix now. Now, how do we do research on dust, interstellar dust in space? Well, so what the astronomers do is they take all these pieces of the puzzle. First of all, the starlight extinction, polarization, infrared emission. They also look at what is in the gas in the interstellar medium, and they assume that what is not in the gas should be in the dust. Oh, there we are again. Good. So they do this over kiloparsec distances, long distances. And when they do that, they get a model. They typically have a model of the size distribution of the dust and also the composition of the dust. Typically, it's a power law distribution between 0.0, like 10 nanometer and a few micrometer. And we have silicates and carbon. And what you can see here on the horizontal axis is radius of the dust. Here we have 1 micron, and here we have 1 nanometer. We have a lot of small dust particles and very few bigger dust particles. So we have this size distribution here, a lot of small particles and not so many big ones. We have here measurements by in situ spacecraft, and then we have astronomical observations. I'll go into that a little bit further in one of the next slides. I would like to highlight one way of observing dust more close by with astronomical measurements. And for this, I have to go back to Zurich again to this guy here. Brian May is very inspirational. Now, he started a PhD in the 70s on cosmic dust science. Then he started to play guitar more and more and more. And at some point, he had to stop his PhD. Luckily, 30 years later, he decided, I will finish that PhD. And I think that's only possible in dust science, I guess. I don't know. But in any case, he finished his PhD in 2007 or 2008, and then 5 years later, together with his supervisor, he wrote a very beautiful paper. It is about an improved model of the infrared emission from the zodiacal dust cloud, cometary, asteroidal, and interstellar dust. So what they basically did is they made a model in the computer of infrared emission of 3 components of dust in the solar system. And for the first time, they also took the interstellar dust that is passing through the solar system. They compared it to data from spacecraft like COBE and IRAS, and they said that their most important result is the detection of an isotropic component of foreground radiation due to the interstellar dust. And they also advised that the next step to take would be to have a look at the time variability of that component. And actually, we have the model to have a look at that, but we should compare it to data if that's possible. So having said this, we also have measurements in space with satellites, and the first instrument that ever detected in space interstellar dust in the solar system that is passing by is the Ulysses dust detector in 1993, and that was actually our supervisor Eberhard Grün who did that. So how it works basically is you have a big bucket in space that is gold coated, then you have a particle that impacts, and the particles ionize and vaporize, and the amount of ions and electrons that you can catch in your detector depend on your impact velocity and your mass, as you can see here from this equation. And so in this way, you can have like a mass distribution. You also know a little bit the direction because you know in which direction the instrument is pointing. If you have a couple of grids here in front, they had only one and it had a lot of noise. But nowadays you can make better ones. And if you have grids, you can sense the surface charge of the particle. And if you have 4 of them, you can actually try to, or already get the directionality and the velocity. So that is very helpful. So these instruments have been developed more and more and more. And also, if you separate the ions a lot with a big voltage, then you can do mass spectrometry and you can get the composition of the dust particles originally. Of course, you have to calibrate these things in the laboratory. This is what we do with a dust accelerator. This is an example of a dust accelerator in Germany, in Heidelberg. There's another one in Boulder here in the United States. And the one of Heidelberg has moved to Stuttgart. You start with a dust source with dust inside. You accelerate it up to 80 kilometers per second for the smallest particles. You can select them with a particle selection unit. And in the end, you have a vacuum chamber here where you can put your instrument. This is a Cassini cosmic dust analyzer that has been analyzing the composition of many dust particles. And of course, you also need to make dust for flying it. And this is our latest attempt, unpublished material. This is fluffy particles coated with polypyrrole by one of our students who did interdisciplinary work between my group and another group at the ETH in Zurich. So for the interstellar dust, we have 3 main measurements. One is Cassini that has been measuring the composition of 36 of these particles with such an impact ionization dust detector. Then we have antenna measurements, which I call serendipity measurements because they were not made to detect dust. It was just by accident that it happened. Basically, you have these antennas on the spacecraft, and what happens when a particle impacts is exactly the same as with a dust detector. So the particles will ionize, and the ions and electrons will fall back on the spacecraft or induce a charge, and this will give you a little spike in the antenna signal that is normally meant to measure plasma waves. So here we see again the combination of dust science and plasma science in one instrument between 2 divisions. The advantage is that you have a lot of impacts because you have a very big surface area. The disadvantage is it's not a dust detector, so you don't have precise measurements. But it's not a nice addition. Then we have also the Stardust sample return. I was part of this research. They have captured in aerogel 2 particles that were fairly intact and 1 particle that kind of exploded, but they still had some material leftovers. And they had 4 craters in the aluminum, also serendipity instrument actually, 4 craters with leftovers of interstellar dust material. So these are the main missions that have delivered us data, and I think the Ulysses mission was actually the most useful data set so far. We have between 500 and 900 interstellar particles, and you can see already here that our information in situ in the solar system is quite different from what the astronomers have done. And now the question is, why is that? So, of course, instrument sensitivity plays a role, obviously. We are not sensitive to a nanometer dust particle if it's very slow. But we also think that the heliosphere filtering plays a role. So the heliosphere will actually filter out a lot of these small dust particles. Why is that the case? Oh yeah, first thing I want to tell, of course, very logical. If you want to measure a lot of interstellar dust particles, you need to get out of the heliosphere because you will measure a factor of 10,000 more than Ulysses has been able to measure. So we count on the heliosphere missions to do that someday. So the dust dynamics in the heliosphere, I will have to explain that in order to explain this discrepancy. The dust dynamics, they depend on the particle properties and also on the environment through which you're flying. And if you combine spacecraft data and computer simulations, you can already constrain some of the particle properties like fluffiness or composition. So for this, I have to explain you the 3 main forces on interstellar dust. There's first of all the gravity from the sun, gravitational force. And some of these particles will just fly towards the sun and they will be attracted by the sun, and you will have a higher density here. So they come here from this side and they go in that direction. Now, depending on the material from which they are made, they might also be repelled by the solar radiation pressure force, and both forces go down with the square distance to the sun. And so, therefore, it depends totally on what particle you have, whether it will be repelled or attracted if they have the same mass. Now, you can imagine if you fly a spacecraft around the sun, you don't measure anything here, but you do measure something here with this mass, that you can already exclude that it's not a silica particle that is porous. So this way you can retrieve information. But it's not so simple. The dust particles, actually, they get charged when they're flying in space, and that's why the heliosphere physics comes in, actually. So they will be bombarded by electrons and ions that will change their surface charge, and also secondary electron emission. When an energetic electron impacts, it can kick off another electron. And this will lead to an equilibrium surface potential that is typically 5 volts in the solar system and 0.5 outside. It also depends on the dust properties. If they're fluffy or if they're compact or if they're silica or carbon, then also the charging will change a little bit. And from this, actually, we can already learn a little bit. We learned, for instance, that the Ulysses particles, the big ones, are probably fluffy and the smaller ones are probably compact. And charged dust moves through a dynamic heliosphere and its magnetic field, and therefore it will encounter a Lorentz force and it will change with the solar cycle. Now, the solar cycle is 11 years, but the magnetic solar cycle is 22 years. And as a result of this, the dust particles will actually go through a focusing phase or a defocusing phase with respect to the solar magnetic equatorial plane. And this is only 7 degrees different from the ecliptic plane. So basically, every 11 years, we can measure interstellar dust in the solar system a lot. And every other 11 years, we have bad luck. Now, the next time that we have a focusing is here in 2030. So if we miss this chance, we'll have to wait until 2052 before we can measure it again, at least the small particles. And this is a message that I definitely would like to give you. We have to be ready for them. Now, the particles, Lorentz force depends on the charge to mass ratio. And for very small particles, you have a lot of charge and little mass. And then the really tiniest particles, they will not even be able to get in the heliosphere. So they are blocked outside. And this is the whole reason why we have this big discrepancy between the heliosphere, between the dust measurements inside and the astronomical measurements outside, or at least it's probably one of the main reasons. If the particles are intermediate and they can get in, then they will, but they are still small, then they will have weird trajectories that are unpredictable. They will be a bit more like this, and they will create rolling waves that are rolling into the solar system. But they are interesting because you can measure them and you can learn from the dust by this. This is a little simulation I made to play with, just a tiny particle of 1 nanometer. It gets picked up by the solar wind immediately and it behaves just like a pickup ion. So we have actually already a connection with the heliosphere sciences and plasma sciences, because dust is actually just a huge, very huge ion, I would say. This is another thing that I just played with. Here you have Jupiter. Jupiter has a moon, Io, and Io is spitting out volcanic material. If you have a tiny volcanic particle of 10 nanometer and you do it in the direction of the Earth, during exactly the minimum of the solar cycle that has a focusing phase, then you can actually reach quite far distances, even almost to the Earth. So who knows? We would have to spit this out a bit further, but who knows that actually Jovian dust gets on the Earth. Now, Ulysses has a lot of measurements, and the issue is with Ulysses, here on the top we have rotation angle, so the direction in which the instrument was looking. On the bottom we have the flux, so how many particles we are capturing with time from 1992 until 2008. And the colors are the simulations, and the bars are actually the data. And what we found is that we could either fit the first part for the rotation angle, but then here we have a rotation in 2004 of the direction from which the dust was coming. Or we could simulate that one in the end, and also the increase in the flux that we have here, but then we have an overshoot here in the simulations with respect to the data. So the hypothesis we had is that we have been simulating so far only the inner heliosphere, but we are missing the outer one. But the particles, in reality, they go through both regions. And we know that in the outer region, the particles will have a higher charge because of the temperature in the heliosheath that is higher. So here you see again heliosphere sciences, dust sciences. And it could be actually that the outer part might have been blocking the dust particles, while in our simulations they were still getting through. So for this reason, we started this project where we are trying to go to find a fit, including the Helios sheath. And yeah, the nice thing is if we can find a fit, then the larger particles should be fluffy. That's one conclusion. So right now we are doing simulations of dust. We are interacting with the heliosphere scientists. We're using their model. But opposite, we also have our data. So far, the heliosphere scientists have been using cosmic ray data, plasma data, magnetic field, and so on. But now, by putting the dust in the models, we can actually also use the dust as a constraint, as a boundary condition for the heliosphere scientists, and that is new. Of course, this is under restrictions that we have enough data. That's the big point. In the end, if we do this, we can also apply that to astrospheres for exoplanets. We can hopefully also constrain the dust properties like the fluffiness, and we can hopefully use these dust data to also constrain heliosphere properties. So you see here that we have a very nice synergy between dust and heliosphere science. Yeah, so I told you already in 2030 there's going to be the next focusing phase of the solar cycle, and we have to be ready. But are we ready? What are our needs? Well, first of all, the needs are the science questions. We have a lot of science questions, and I summarized them in a white paper that I'm going to publish also in the journal RASTI. And for the micron-sized ones, questions are like, what is the gas-to-dust mass ratio in the interstellar medium? Is the dust coming from another direction? What's the composition, morphology, etc., etc. Now, for the large particles, actually, we could also collaborate with meteor scientists. And the reason is this, that we are having dust detectors in space. And if we have a large enough surface, we can also measure the big interstellar dust particles. We had a few of them with Ulysses, but we would need long integration times and large surfaces. And at some point, we should be able to put our data together with the people who do radar measurements of meteors. There are some who claim that are interstellar ones, and that is a topic that is quite controversial and still being researched on. But that is another example of cross-disciplinary science, radar together with in situ measurements. Then we have the submicron particles, where the dust dynamics with the heliosphere become very important. What is the solar cycle dependence of especially the Helios sheath filtering of the dust? Is there a relation to pick up ions? Is the thickness of the Helios sheath sometimes thicker or thinner? What is the surface charge of the dust? And then finally, we have the nanodust. How much is filtered out? How does it depend on the solar cycle? Is there a pileup in front of the heliosphere? And how does that affect the physics of the heliosphere? Would that create an extra pressure for the pressure balance of the heliosphere? So what is the role of the dust for astrospheres and for heliospheres? And what is the role of the dust in the history of our planet while going through this galaxy? All right, so I'm going to go to the current missions. There are a couple of missions that are important for interstellar dust science. I'm going to mention only two of them because for the other ones we don't have results yet that I can show here. So the first one is New Horizons, which is a very beautiful, also cross-disciplinary mission. They do heliosphere science right now at the moment, but it was originally very planetary. But it has a dust counter that was made by students, actually, a student dust counter. And they have been measuring dust particles, and they did also some simulations of that. We have done some interstellar dust simulations, pretty horizontal, pretty flat, because the particles are quite big for which we simulated them. But you see already here that there are more particles than they expected. And this could be either an extended Kuiper belt or we don't know. Then another example is the WIND mission with our serendipity data. You see here a very complicated curve. So it has a lot of ups and downs. This is time here, and this is the flux of the particles that was measured with the antennas that were actually not meant to measure dust, but they did it nevertheless. And you see here the cycle. This is because of the Earth that turns around the sun. As you can see, we go around it. Once a year we go with the dust, and once a year we go against the dust. So that means that once a year we have a lot of flux and also more sensitivity. And once a year we have very little sensitivity and little flux for the smaller particles. But then you also see that here you see an increase in the data, and that is actually because the focusing phase of the solar cycle is in 2010. So in these serendipity data that other people would have thrown in the dustbin, there's actually a lot of information about the dust. Now, it's not so simple. You see a lot of other stuff here that is not easy to explain. And actually, my postdoc, Leonard Baumann, is working on that. He has been cleaning up quite a few of this data. There's things happening in space. The antennas have broken. then the one antenna broke again, and you have changing data rates and so on. So it's really not easy to do that, and I hope in the future we will master the art of antenna measurements very well. Yeah, near future missions. There are some missions coming up. As you can see, this is here a slide that my postdoc has been putting together. There were quite a few missions in the past that had dust detectors, and here around 2010, 2020, there were not so many, but in the future there will be a couple of more. The first one is Destiny Plus. That's a mission from JAXA and DLR that has a dust analyzer. It has a focus on phyton research. Phyton is an active asteroid, which is between comets and asteroids, and it will measure also interstellar and interplanetary dust. It has a time of flight mass spectrometer and also a grid in front of it to measure the direction from which the dust is coming, which is really useful. And then we have also this mission here. IMAP is a very beautiful example again of cross-divisional science. It has a dust detector on board, but it has also wonderful heliosphere science to do. They will have one of the best compositional analyzers on board, with which they will measure a lot of interstellar dust also. Then we have here, this is quite a dense slide, but I definitely wanted to mention it. We have, apart from IMAP, also Europa Clipper. And Europa Clipper is going to Jupiter. And coincidentally, Jupiter, at that time when Europa Clipper will arrive, Jupiter will be moving into the stream of interstellar dust. So that means that we have a higher flux, but we also have the focusing phase of the solar cycle. As you can see here, the smaller particles in 2030 will increase by a factor of 10 with respect to normally. So actually, to my opinion, we have to use that opportunity to take measurements over there. So this is a very good reason why we could, for instance, turn on, if that's possible, turn on the instrument before we arrive at Jupiter. And another reason could be that Jupiter has this little moon Io that is spitting out dust, and in whether this dust will fly across the ecliptic or fly up and down also depends on the solar cycle. We did two very simple simulations, really simple, from Jupiter spitting out dust in the focusing and defocusing phase. It would be really interesting if SUDA could measure this beforehand. So it's a very good opportunity in 2030. Now, what would be really interesting in the future would be a future mission. So what we did in Europe is we submitted a mission proposal called the Dolphin mission. And it was meant to measure this increase of interstellar dust here in 2030 and 6 years later. It wasn't selected because it was too expensive. It was interplanetary and so on. But it would be certainly great if there would be another opportunity. And maybe one of the opportunities could be the Gateway. Again, cross-disciplinary, this is human spaceflight, but we can use it for science. And if we could get a dust detector there, it would be quite useful. You see here again that for very small particles, there's an increase in 2030. And this, if we can measure that, that means that these particles are able to get through the helios sheath. But also important is the direction of these particles. Here you see the latitude in which they are flying throughout time. And you see for different sizes that you have different latitudes. So if we have a grid in front of our instrument, then we would also be able to much better characterize what kind of dust is hitting the detector. Apart from the Gateway, this is, of course, a very beautiful mission concept. It's the Interstellar Probe. It's kind of a follow-up concept for Voyager to fly out of the solar system. And obviously, we are super enthusiastic about this mission as a dust scientist because of what I explained. We would measure a factor of 10,000 more particles than Ulysses has been able to measure with state-of-the-art technology that exists today and didn't exist 30 years ago. We would have mass spectrometry. If we could have a grid, we would have directional information, charge information, and if you at the same time also have measurements of the plasma temperature, the plasma density, and you put that together, you can even determine if the particles are fluffy or not. And so that would actually benefit and also the astrophysics. My postdoc here has done simulations and predictions for what this mission would be able to measure, and we will publish that hopefully in the first half of this year. The important needs for the future are, first of all, a multi-mission approach, long-term monitoring of dust dynamics, synergies between different instrument types. We should optimize serendipity instruments and dust and plasma on one single mission. This is a video that seems to, I will have to see if that works here. Yes. So here is a video of a few missions that have been flying in the past to different regions in the solar system. You see here the Voyagers going out and Ulysses here in the middle. And as you know, the dust problem is a time variable problem, but it's also a spatially variable problem. So how do you learn about it, and how do you distinguish between the two with only one mission? What you actually need is a collaboration between different missions, a synergy between different missions. And that is what I would like to advocate. We need to work together. The second thing that we really need is definitely a dust telescope on one mission, and preferably long-term monitoring of dust. As you know, it's with the solar cycle. Synergies between different instrument types, and just an example of that is Stardust has brought back particles with this aerogel collector here. But if we put in front of that a grid that can measure our direction, the time of impact, and the velocity, then you would have much more information, and you would even be able to distinguish between different comets if you are focusing on certain comet flybys or stream flybys. Efficient use of serendipity instruments. It would be great if we can improve the way that we work with the antenna measurements, and if we can optimize that, because it's a very rich source of information. And finally, dust and plasma measurements on one single satellite is very useful, for instance, if you want to figure out if the dust is fluffy or not. Having said this, again, dust to dust, and thank you for your attention.
Thank you, Dr. Sterken. Before we move to the conversation part of this event, are there any pressing questions about this presentation that one of you in the audience here or online would like to ask?
Yeah, so Jupiter is flying around the sun. And once a year, it will fly behind the sun. And behind the sun, the biggest particles will be more subject to gravity. And because of this, there is behind the sun, as seen from the dust, there is a higher density. It's actually what I showed you in one of the first slides. I'll have to get back to the dynamics here. This one. So the particles that you're talking about, the big ones, are actually more subject to gravity. So that if Jupiter is going through this region, there will be an increase of those particles. So yeah, very good question.
Yes, why don't you take the microphone?
Okay, sorry. Solar cycle 24 was like the weakest solar cycle in the space age. Did you see something? I know, I mean, I guess it's in solar minimum that you get all these particles, more particles through. Did you see something strange in that solar minimum, that, you know, many more particles are coming from elsewhere or anything like that?
So I'm not a heliosphere scientist. Solar cycle 24 was in 2010, or? Yeah. Yes. It's the only data that we have available. So I don't know if it's strange. Yeah.
So I heard there is one question online. Is that going to be coming? Jim Green?
Yeah, I just was curious about both Voyager 1 and 2 have a plasma wave instrument, obviously making measurements prior to exiting the heliopause, but they may have been working outside the heliosphere. Have you looked at any of the dust signatures that they might have measured?
Yes. So the Voyagers are outside. I will hear actually a talk about this next week with the progress, and I know that they're writing a paper. But one of the issues with the Voyagers is that there's very little time for downlink for the data. So we only have a few particles per, I don't know how much. It's difficult to do good science, but I'm looking forward to hear more about it in the talk next week, and we are going to collaborate.
What was the name of the conference next week? I'm sorry.
It's a New Horizons team meeting, actually.
Thank you.
Okay. So let's come to the conversation part. Sit down. this was a very exciting interdisciplinary presentation. I wanted to ask you, you did not talk much about the planetary part. When I started working on calibrating a dust detector for Cassini, and even now, it seemed to me that dust science was always considered mostly a planetary subject. Can you elaborate on that? What phenomena are there that would drive the people to believe this is mostly a planetary science?
Yeah, that's a very good question. So I think in the first place, the dust that we have in the solar system is not the original dust that was there when the solar system was born. Actually, the dust has a fairly short lifetime because of several dynamical aspects. It will spiral into the sun and so on. But this dust is actually dust that comes from comets and asteroids. And the comets are basically time capsules that keep the dust that was originally there and from which we can learn about the history of the solar system, from what solar system objects are made. Apart from this, yeah, there's plenty of planets that are ejecting dust or so. So for instance, Enceladus has an ocean and Cassini has flown through the plumes. This can be considered as planetary science, of course. If you use the dust to measure the composition of the ocean of Enceladus, that is really cross-divisional. It's not just dust, it's the composition of that ocean. And then third, we have these planets. Basically, every moon that doesn't have an atmosphere has a cloud around the moon with dust because the moons are impacted by particles and so there are ejecta. So basically, you would be able to measure the composition of these planets, of the surface, using a dust detector by flying around it. Historically, of course, dust science has been first, I think, for the safety of the astronauts. They wanted to know if the astronauts would be safe out there. We've seen it recently in December that there was a particle that probably impacted on the Soyuz, and there was a leak on the Soyuz. And coincidence or not, but this was exactly in the middle of the Gemini meteor shower. So these particles would impact at 35 kilometers per second. Now, that's not planetary science, of course, but it's certainly, again, cross-divisional.
Yeah, that's certainly correct. Interesting would be to elaborate more on the interface between, let's say, heliophysics and planetary. Planetary bodies are mostly on Keplerian orbits. I think you mentioned a few times also there are other forces that work on dust. Can you elaborate a bit more on these other forces and when they become important?
Yeah, so I told you about these comets that are turning around the sun, orbiting around the sun, and the dust that comes off normally would stay on the same orbit. And when the Earth crosses that orbit, we get this meteor shower that can damage our spacecraft. And these are gravitationally bound particles, but of course they will be also subject to solar radiation pressure force. So there's a certain mass range between which these particles have a lot of radiation pressure, and those particles from these comets will be diverted. And most of them actually will be ejected from the solar system. We call them beta meteorites by the solar radiation pressure force. And then third, I think the solar radiation pressure force has a little component because the speed of light is finite. And it has this, in the frame of reference of the dust particle, it has a little drag component. And so that's why the particles are spiraling down to the sun and have a very limited lifetime. Let me think about other forces. Of course, the electromagnetic forces about which we have been talking. We talked about the electromagnetic forces for interstellar dust, but it also exists for the Jovian dust, like these dust streams from Io and also from Enceladus. They are electrostatically accelerated to very high speeds, and then they behave like a giant pickup ion. There are more forces, there's this Poynting-Robertson and so on and so on.
And with these other forces, electromagnetic forces, we're squarely already in the heliophysics realm. And heliophysics, of course, the science of the sun and its interactions with the Earth and the solar system. Speaking of the sun, you showed a slide earlier of all the spacecraft that would be measuring dust. I noticed an omission, Parker Solar Probe, which goes very close to the sun and there's a lot of dust. Can you talk more about what's going on close to the sun in terms of dust?
Yes, I didn't put Parker Solar Probe in there because it doesn't have measurements of interstellar dust, but obviously for interplanetary dust, it's a very important mission. Closer to the sun, we have a lot more particles, that's clear. We have a lot more comets that are coming there, and we have also the dust particles that are spiraling in. The particles are flying much faster, so they will collide and they will generate a lot more particles. And as far as I know, Parker Solar Probe has been measuring a lot of particles, but since you are the Parker Solar Probe mission project scientist, I think you can. Oh, okay. Yes. Yeah. Okay. So there are also antennas on the spacecraft, I believe. Oh, there we are. Okay. Would you like to expand on this?
As the Parker Solar Program scientist, maybe I should say a few words. So Parker, of course, a brilliant mission. We already had 14 successful encounters with the sun. The 15th is around the corner, and we survived them all, despite the fact that there is a lot of dust close to the sun. And what you can see here is a movie of what we see sometimes when we're close to the sun and flying through the debris cloud that is the zodiacal dust close to the sun. And there, what happens there is the dust impacts the brittle heat shield that keeps the spacecraft cool enough so it can work. And then there's a bright source of light from all the material that gets ejected to the sides, and that flies through the field of view of this wide view camera that we use to image the solar wind near the sun. And there are times when we get so many impacts that we hardly can see through this cloud. So we are really dominated by this dust. And also the antennas of Parker Solar Probe measure these impacts on the spacecraft. Another serendipity measurement, as you mentioned earlier. And that certainly also shows that there's a lot of dust nearby, and there's a lot of studying of this. Maybe another interesting aspect that we've observed, you mentioned the Geminids earlier, which has as a source the Phaethon asteroid. We actually imaged the flux tube of the dust with Parker Solar Probe. I don't have the picture here, but it's a fascinating measurement. And another thing that we imaged with Parker Solar Probe is the dust torus in the orbit of the planet Venus, going all around the sun where Venus would go. We can also see that there is apparently a dust torus around it. But moving on to maybe another aspect, we also mentioned Soyuz. So we have dust, of course, also entering the Earth's vicinity. Can you talk about what happens and what do we need to be careful of about the dust that goes really close to the sun, to the Earth?
Okay, thank you. Before we go on with that, I have a small question for you, actually. Did you expect this to happen for Parker Solar Probe?
So there was a lot of studies of dust done. The spacecraft has been studied whether it survives the encounters. The highest risk is penetration, I think, of the coolant loops that are on the outside, somewhat exposed. There's a very low likelihood of these large particles. What we mostly get are these very small particles. What has also been taken into account is the spacecraft always needs to know which way it's oriented, because the heat shield near the sun needs to point towards the sun to keep it cool. And there's redundancy in that. We have star fields, star trackers. These are sometimes blinded by these effects. But there's also an internal gyro that keeps the knowledge of the orientation. And the star trackers always recover really fast from that, so there's really no risk from that. So in some sense, yes, but in some sense, I'm not sure whether the WISPR team was aware of the debris that would fly through their field of view, and there's not much one can do. Maybe the white coating of the heat shield is not helping in the brightness of these things. Good question.
Okay. Yes, sure.
I have a question. I don't know if you can hear me.
Okay. Yes, we can hear you.
With the various different particles that are hitting the antennas and the various different parts of the equipment, I was just wondering if there are any electromagnets that are being used to protect them from the particles, and if not, why?
I don't know whether acoustically you heard exact. Can you repeat the specific effect that you were asking?
Yes, with the antennas being hit and various different pieces of equipment that are being hit by the particles that are moving, are electromagnets being used to protect them? And if not, why?
No, that is certainly not the case. The dust is usually so small that it will not do much harm. We had a little bit of damage to one of the instruments that uses foils, but that is manageable. But we
Okay,
have no specific way of avoiding these impacts. I think that
okay,
that
thank
may be
you,
challenging to achieve.
thank you.
Okay. Yeah. So, well, for the Earth. Okay, the Earth. Yeah, when the particles go to the Earth, of course, there's a gravity, so they will be attracted by the Earth. You might also have shielding, and finally, there will also be particles, first of all, that are dangerous for the astronauts, but also they will enter the atmosphere. A small particle will actually slow down very slowly and will land on the rooftops of the people. There's another musician, John Larson, who has even been collecting those and made a book about it, very beautiful. Bigger particles, they will slow down and they will burn up in the atmosphere. These are the meteors. You can do a lot of wishes, and that meteoritic smoke might even create noctilucent clouds, so it can have an impact on the weather. Yeah, and then finally, of course, there are the big ones that might give damage, the meteorites and the big impacts. But there will certainly also be an influence on the atmosphere, and not only the particles from natural dust, but also our space debris. And there was even a paper recently, a year ago, I think, from a professor in Braunschweig who wrote about the impact of rockets that are returning on the atmosphere composition. And I've seen that this paper has been cited already a couple of times, and it seems that it's that they're worrying about it.
And I think with this, we have covered all aspects of the science mission director, from astrophysics, planetary, heliophysics, and earth science. And I think that's a good time to end this. Thank you very much for being with us today. And thank you everybody online and here for listening.